Hello and welcome to my LeetCode problem tutorial video. Today we're going to talk about a problem called unique paths. We're going to look at the problem description and an example. Then we're going to explain two solutions, dynamic programming and mathematical. In dynamic programming, I'm going to explain top-down and give an example and the code and explain why it's inefficient and should never be used. Then I'm going to explain top-down with memoization, an example, the code, and the time complexity. And finally, I'm going to show bottom-up with an example, the code, and time complexity. The next solution I'm going to talk about is mathematical solution, or explain the mathematical solution with two ways, finding permutations using factorial and using n choose r. And then I'm going to show you the code and show you how to prevent integer overflow. And finally, I'm going to explain the time complexity. So first, let's look at the problem. You're given an m by n grid where a robot is located at the top left. You have to find out how many ways the robot can reach the bottom right. The robot can only move right and down in one step, and it can't move diagonally. In this example, m is 7 and n is 3, so you're given a 3 by 7 grid. The robot starts at the top left. One way it can reach the bottom right is if you go all the way right and all the way down. Another way you can reach the bottom right is to go 4 right, 3 down, and 4 right again. Another way is going all the way down and all the way right. There are in total 28 possible ways, so you return 28. The first solution I'm going to talk about is dynamic programming with top-down. You recursively traverse every single path and keep track of the index through the parameters of the method. If you go out of bounds, then you return 0, and if you reach the end, you return 1 because you reached your destination. If none of those are true, you return the sum of the number of paths if you go down and the number of paths if you go right. Let's look at an example. You're given this 3 by 3 grid and you start at the top left. Note that the zeros in each of the boxes aren't stored by the algorithm itself, it's just used for visualization. So you're not out of bounds and you haven't reached the end, so you return the sum of right and bottom. You first go right, and the same is true for this one. You return the sum of right and bottom. You go right again, and then you return the sum of the right and bottom, but you go right and then see that you're out of bounds, so you go back with a value of 0. Now you go down and go right again, but you're out of bounds, so you go back. And when you go down, you see that you reach the end. So this one returns 1, and you go back. The sum of the right and bottom is 1, because going right results in 0, and going down results in 1. So that returns 1. Now this one, going right returns 0, and going down returns 1. So the amount of paths here is 1. This square finally finished right, so now it goes down. And then this one goes right to calculate the amount there. And because we haven't stored the previous value, we have to traverse every single possibility again. So we go right, we find there's 0, we go back, now we go down, and this returns 1, so we go back with a value of 1. This returns 1, which is the same value as before, but the computer doesn't remember that. So now this square traversed everything to the right, and now it goes down. And this one first goes right. This returns 1 because it reached the end. And going down returns 0 because it goes out of bounds, so it just returns with 1. And this square, the sum of right and down is 2 because 1 plus 1 equals 2. So this returns 2, and this finally traversed all the possibilities to the right and all the possibilities to the bottom, so it returns. And now we go down and we traverse every single path again except down. You can probably see why this method is inefficient. So let's just skip forward all of this and just look at the code. Program it. We first create a helper function that keeps track of the index and the parameters. We first check if it's out of bounds, and if it is, we return 0. If you have reached the end, however, you return 1. But if none of those are true, you return the sum of right and bottom. And finally, the main function calls this helper function with 0, 0 as the starting index. This method is inefficient because it calculates this number of paths from the same square a bunch of times. It doesn't remember the answer that it got before, so it calculates it again. Let's take this example over here. Given a large number of m and n is a large number 2. We start at the top left square and calculate the amount of paths from m and n as 1, 1. And then after we calculate all of those paths, when we go back, we have to calculate all of those paths again. And m and n can be really big, so we're practically doing the entire problem again. The second solution I'm going to talk about is top-down with memoization. This is the same as top-down, except it remembers the previous answers it got, so it doesn't recalculate any old ones. We store all previous values in a 2D matrix size m by n, and each index I and j represents the number of paths at that location. Initially, everything is stored to 0. So let's say we calculated all of those paths same as before. Now we go down and we try to go right. But we see that we already calculated this value before, so we just go back with a value of 2. Now we go down and right, and we also calculated this value before as 1, so that returns 1. And when we go down, it's out of bounds, so it returns 0. So this value becomes 1, and this becomes 3 because 2 plus 1 is 3. And the final value is 3 plus 3, which is 6. So it returns 6. To program it, we first create an int array, a 2D array called memo, size m by n. And then we do the same thing as before. We check for out of bounds, and we check if we reach the end. And an additional check where we check if the memo int array already had the value we calculated before. And if it does, we return that. And if none of these are true, we just return the sum of the bottom and the right. And finally, the main method returns the helper method with index as 0, 0. The time complexity is m times n because it calculates each square once, and the amount of squares is m times n. The next dynamic programming solution is bottom-up. Usually in bottom-up, you solve the smallest subproblems first, and then work your way up from there. The smallest subproblem here is starting at the ending square, where there's only one possible way to reach the end, which is just say put. And then we can go backwards and just put the value as a sum as the bottom and right. We first put the ending square as 1, and then we go to the square before that, to the left of that, and bottom is 0, right is 1, so we put that as 1, 2. And the same for left of that. And then now we go to the next row, last column, and put that as 1 because right is out of bounds and bottom is 1, 1 plus 0 is 1. Then the next square is 1 plus 1 because bottom plus right, so put that as 2. And we simply work our way backwards from there, and finally we arrive at a value of 6, so we return the index 0, 0 of this grid. We create our grid first of size m by n, and we set the last square to a value of 1. And then we work backwards with these two for loops, and we put it as the sum of the bottom and the right. If bottom or right is out of bounds, then we just do the other side. And if it's the last square, then we don't do anything because we already put that. And finally, we return the 0, 0 index. The time complexity is also m by n because you look at each square in the grid, and the grid is m by n. The next solution I'm going to talk about is a mathematical solution. If we take this 3x3 board and one example of how to reach the end, we can get this. Or another way we can reach the end is this. If we take apart each of the lines, in this solution we get 2 vertical lines and 2 horizontal lines resembling, and each vertical line resembles a right move, and each vertical line resembles a down move, and each horizontal line resembles a right move. We have 2 vertical lines and 2 horizontal lines. If we take apart the lines of the other path, we get the same number of vertical and horizontal lines. So this problem can become how many permutations of these 2 sets of lines are possible. The amount of vertical lines is m minus 1, and the amount of horizontal lines is n minus 1. If we take this example, this 3x3 grid, the amount of solutions is 6 because these are 6 permutations. The first one resembles going right twice, then going down twice. The next one to the right of that resembles going right once, going down once, going right once, and going down once, and so on. So if we go back to the previous one, take circles instead, the amount of permutations of these circles is 4 factorial, or factorial. N factorial just means n times n minus 1 times n minus 2 all the way till 1. So 4 factorial would be 4 times 3 times 2 times 1. But if, let's say, 2 of them are red, now suddenly there are less permutations, because if the 2 reds are next to each other, they're still counted as the same permutation, even though the red circles are different red circles but the same color. So in this case, we do 4 factorial divided by the number of duplicate circles, which is 2 factorial. If, let's say, 2 of them are red and 2 of them are blue, now there are 2 duplicates, so we do 4 factorial divided by 2 factorial, resembling the number of red duplicates, multiplied by 2 factorial, resembling the number of blue duplicates. So if we go back to our line example, there are m minus 1 vertical rods and n minus 1 horizontal rods. The number of rods in total is m minus 1 plus n minus 1. So it's m minus 1 plus n minus 1 factorial divided by the number of vertical duplicates, which is equal to n minus 1, and the number of horizontal duplicates, which is equal to m minus 1. So the formula we get as our final answer is m minus 1 plus n minus 1 factorial, all of that divided by n minus 1 factorial times m minus 1 factorial. The next way I'm going to show how to get this formula is using n choose r. N choose r is a formula that basically tells you how many ways can you choose r elements out of n total elements. For example, using these circles, there are 4 elements, and I want to know how many ways I can choose 2 of these circles. So it becomes 4 choose 2. And this is one way I can choose. This is another way. This is another way. And so on. So 4 choose 2. The formula for n choose r is n factorial divided by n minus r factorial times r factorial. So 4 choose 2 becomes 4 factorial divided by 4 minus 2 factorial times 2 factorial, which is 6 if you calculate all of that. So using our lines, we can simplify this to the amount of total lines there is, n as n, and we choose either m minus 1 or n minus 1, or the vertical or horizontal lines. In this example, we can choose last 2, we can choose these 2, and we're basically choosing the indices of some lines, either the vertical or horizontal. If we choose these 2, the vertical lines goes at these 2 indices. Example, the vertical lines goes at these 2 indices. So it becomes an n choose r problem. The amount of lines in total we can say as n, and the amount of vertical or horizontal lines we can choose becomes r. There isn't a difference if you choose n or if you choose vertical or horizontal, but I'll explain that later. So n will be m minus 1 times n minus 1, because that's the total number of rods. The amount of vertical rods are n minus 1, so it becomes m minus 1 plus n minus 1 factorial divided by m minus 1 plus n minus 1 minus n minus 1, which can be simplified to m minus 1 factorial times n minus 1 factorial. If we chose m minus 1 as r instead, it would simplify when we do m minus 1 plus n minus 1, so we'll get the same answer. To program it, we first create our factorial method, which can be done like this, and then in the main unique paths method, we return factorial of n minus 1 plus n minus 1 divided by factorial of n minus 1 times factorial of n minus 1. However, if you run this with numbers even as small as 10 by 10, you will get an answer of 0. Why does that happen? Because the factorial gets really large numbers. So you get integer overflow, and in Java it rolls around, so you'll get some strange answers. So to prevent overflow, you have to figure out how to simplify it. First of all, we can just replace every int with long, but that still doesn't work. So if we take this example, then we see that 4 times 3 times 2 times 1 appears in the numerator and the denominator. So if we cancel out the 4 times 3 times 2 times 1 from the numerator and the denominator, we get this new formula. And this is a much smaller number than what we got before. It's the same number, but we use much smaller numerator and denominator. So in the factorial, we now introduce a lower bound, because we do, in the previous example, we did 7 times 6 times 5 with a lower bound of 4 because we canceled that out. And then now we check the larger number and then cancel that out from the denominator by introducing a lower bound in the numerator and just removing it from the denominator entirely. The time complexity is O of n plus m because factorial takes O of n for n factorial, and we calculate the factorial of n once, m once, and m or m, depending on what you choose, once too. So the time complexity becomes m plus n plus the minimum of n and m, or just O of m plus n. Since this is m plus n instead of n times n, this is faster than dynamic programming. This is the last solution I'm going to talk about today. I hope you enjoyed this video.